Hello, in this video we are going to look at this question on rotational dynamics. It is from the Catholic mock of 2024. The question says a uniform thin rod AB of mass m and length 2a is free to rotate in a vertical plane about a smooth fixed horizontal axis through a point x on the rod where ax equals 2a over 3. 1. Use the parallel axis theorem to show that the moment of inertia of the rod about the axis through x is 4 over 9 ma squared. Initially, the rod is vertical with B above A. It is then displaced slightly from this position. Show that in the ensuing motion, 2a d theta dt all squared equals 3g into 1 minus cos theta, where theta is the angle AB makes with the upward vertical. 3. The maximum angular acceleration is 3g over 4a. In the first part, we draw the rod as a single line for simplicity. So the end A and the end B are indicated, then the center G of the rod is here. The rod is said to be of length 2a, so this is a unit and this is a unit, but the point x where the axis is somewhere here. So this is x, and x is in such a way that ax is 2 over 3a as the question specified. It means that from x to g, that distance is very crucial in this calculation. The distance from the axis to the center of gravity of the body that is doing the rotation is always of prime importance in your calculation. So if you subtract 2/3 a from the distance from a to g, which is a, you get a over 3 as the distance between x and g. In the first part of the question, again, we have been asked to use the parallel axis theorem to show that the moment of inertia of the rod about the axis through x is 4 over 9 ma squared. So by the parallel axis theorem, the moment of inertia through the axis x should be equal to the moment of inertia through the center g plus the mass of the rod, which is simply given as m, times the square of the distance between the center of the rod and the axis at x. That distance is a over 3. So a all over 3 all squared. Now, the formula booklet provides the moment of inertia of a rod about an axis through the center as 1/3 the mass is m, times half the length, and the length being 2a, half of the length is a squared plus m into a over 3 squared, which gives a squared over 9, and we have 1/3 ma squared plus 1/9 ma squared, and the LCM being 9, we have 3 ma squared plus ma squared, so that the moment of inertia about the axis through x would then be 4 all over 9 ma squared as required. The question asks us to show that moment of inertia is 4 over 9 ma squared. Now, in the second part, we are told that initially the rod is vertical with B above A. It is then displaced slightly from this position. Show that in the ensuing motion, 2a d theta dt equals 3g into 1 minus cos theta, where theta is the angle AB makes with the upward vertical. So in the second part of the question, as a tip here, generally when you see a rotational dynamics question and there is a proof of a statement like this involving d theta dt all squared, know that you are going to use conservation of mechanical energy to arrive that statement. So in our second part of the question, we will be seeking to prove that statement by making use of conservation of mechanical energy. I will first draw the rod, which is said to be vertical in such a way that B is above A, and in that vertical position at time t equals 0, B would be up and A down. Now, since I'll be conserving mechanical energy, which involves kinetic and potential energies, it is important that I should define the 0 level of the potential energy. So I can put it here. So PE equals 0 level. And from there, it is always convenient to put the axis at that 0 level. So if my x is at that 0 level, then the width of the body would be at the center of gravity there, g. From the analysis in the first part of the question, the distance between the center of gravity and the axis, we had it as a over 3. This distance is very important. In fact, it is the most important part of this calculation. If you miss that distance, you would not get anything right in the calculation. The distance actually between the center of gravity of any body that is rotating and the axis of rotation is important because it is the radius of rotation by virtue of the fact that the mass of the rod is concentrated at that center. And so the rotation would be as if it is a particular particle of mass m, which corresponds to the mass of the rod that is doing the rotation. So from this position, then we can now put a general diagram for the case where the rod has been slightly displaced and it is now doing the rotation, so that at one point at time t seconds, the rod would find itself in this inclination, where again here we have the axis x and the mass of the rod again is concentrated there, where the distance from that g to x is again a all over 3, and the question tells us that the angle theta that the rod makes with the vertical or with the upward vertical is theta. So at this point then we have the weight of the rod acting vertically down, the mass being m, the weight should then be mg. Now this angle is still theta because it is alternate to this other angle with the upward vertical. So we would be needing the distance from the center of gravity to the zero level, and that distance would simply be the hypotenuse, because this will give us a right angle triangle. Height of g from the potential energy equals zero level would then be a over 3, the hypotenuse of the triangle, times cos theta. That is the new height of the center of gravity g of the rod at this position at any time t seconds. The direction of rotation is this way, so theta dot is in this direction. From here now we can conserve mechanical energy, whereby mechanical energy before must be equal to mechanical energy after. Now, before we proceed, remember that mechanical energy is always composed of potential and kinetic energy. So we have to consider potential energy and kinetic energy in the two cases before the motion starts and at the general position where the motion is already going on. Now, in the case of the initial position where the rod is vertical, kinetic energy is 0 because the rod is not moving at that time, and the potential energy would be the mass times the acceleration due to gravity times the height of g above the zero level. Since g is above the zero level, this value of the potential energy will be positive, so times a over 3, the height of g above the axis, plus 0 kinetic energy as already explained. That will be equal to, now in the general position at time t seconds, we have potential energy to be mg times the height of g above the zero level, and again the potential energy will be positive because g is above the zero level at that point. If g was below the zero level, the potential energy would be negative. So here the height of g above the zero level is a over 3 cos theta. It has reduced as g is falling, so we have a over 3 cos theta as the height of g above the zero level at that general position. Then at this general position, the rod is in motion and the angular speed is denoted theta dot. So the kinetic energy at that point will be half the moment of inertia of the rod about an axis through x times the square of the angular speed at that point. So we get mga all over 3 equals mga all over 3 cos theta plus half into the moment of inertia about x, which we are just from proving the first part that it is 4 over 9 ma squared times the square of the angular speed. And in all the terms we can see that m and a are common, so I would cancel ma from all the terms. Here m would cancel and the square of a would cancel, and then 2 cancels here to give 2, so that on multiplying through by 9, the LCM, we then get 3g equals 3g cos theta plus 2a theta dot squared, and from here 2a theta dot squared should be equal to 3g minus 3g cos theta, so that 2a d theta dt all squared, because theta dot is d theta dt, would be equal to, in the two terms on the right hand side, 3g is common, so that we get 1 minus cos theta when we divide both terms by 3g. And this gives us the proof that we have been asked to execute in the second part of the question. We were asked to prove in the second part of the question that 2a into d theta dt all squared equals 3g into 1 minus cos theta. Now, in the third part of the question, we are asked to prove that the maximum angular acceleration of the rod as it is rotating is 3g over 4a. In the third part of the question, we have to first get an expression of the angular acceleration before we can determine its maximum value. Now, angular acceleration is simply the derivative of the angular speed, and the angular speed, the expression for it is already in this last part of the second part of the question. So 2a theta dot squared, because d theta dt is theta dot, equals 3g into 1 minus cos theta. Now, since this expression already has theta dot, the angular speed, I can then use it to obtain the angular acceleration, because the angular acceleration is the derivative of the angular speed with respect to t. So to have that expression theta dot dot, which is the angular acceleration, I will differentiate this expression with respect to t, so that I get 2a being the constant term or the coefficient of theta dot squared. Then I differentiate theta dot squared with respect to t, and using the power rule, it will give me 2 theta dot times the derivative of theta dot, which is theta dot dot. That should be equal to 3g into the derivative of 1 minus cos theta with respect to t. The derivative of 1 with respect to t is simply 0 minus the derivative of cos theta with respect to t, which we have to first differentiate cos theta with respect to theta, because that is the variable that is there, and then multiply the answer by d theta dt according to the chain rule. So differentiating cos theta with respect to theta instead, because I'm supposed to differentiate with respect to t. Since t is not there, I have but theta, so I first differentiate with respect to theta. That will give me negative sine theta, and then I multiply the result by d theta dt, which is simply theta dot according to the chain rule. Now when you look at both sides, theta dot will cancel, and then we have 4a theta dot dot equals 3g into 0 minus sine theta gives sine theta. And so finally we have that theta dot dot, the angular acceleration, should be equal to 3g all over 4a times sine theta. So from this expression of the angular acceleration, it is clear that 3g over 4a is a constant. So sine theta is what will be determining the value of the angular acceleration theta dot dot as the rod is rotating. The question has asked us to find the maximum value of that angular acceleration. So the maximum value of the angular acceleration will occur when this variable part of its expression is also maximum. And we recall from our knowledge of trigonometry that sine theta always lies between -1 and 1. That means the maximum value of sine theta would be 1. It implies that the angular acceleration would be at its maximum when sine theta corresponds to that 1, its maximum value. So we can conclude that theta dot dot is maximum when sine theta is maximum, i.e. sine theta equals 1. Therefore, theta dot dot max equals 3g all over 4a into 1, which corresponds to 3g all over 4a as required. Thanks for watching. If you are new to this channel, subscribe and activate the notification bell so that anytime I post a new video, you would get the alert and watch. Also share the video to your friends so that they get to know more about the channel, which is very resourceful for your examinations.